Hey, Chem30s, Manchak here. Got a new setup for you this week, and we are going to get into covering concepts C4 and C5 out of the unit that we're currently working on in organic chemistry. So to this point, what you should have covered is you should have finished up concepts C1 and C2, watched the video, gone through the practice worksheets, done a whole bunch of other work on that, including the activity that I put forward with building molecular models. And once you've done that, you should have done your practice quiz and your summative quiz, and then moved on to concept C3, which was a really short concept on aromatics, and then an introduction into distillation of crude oil, those kinds of things. And so today we're moving into concept C4 and C5, and we're going to cover both of these in this video, I hope, relatively quickly for you. So new setup, so I hope it works. I hope you guys can hear me just fine. Let me know, make some comments if you aren't sure of what's going on. So what we are covering in this concept today is we're going to do C4, which is a lesson on combustion and combustion reactions, and then we're going to move into organic halides, including two other kinds of reactions, which we call addition and substitution reactions. For me, the trickiest bits in this lesson, just to give you guys an idea of what I think are the trickiest bits, is going to be understanding the difference between complete and incomplete combustion reactions, as well as, I think the organic halide stuff will be really simple for you, but it'll be the addition and substitution reactions and trying to figure out those that might be a little bit challenging for you. All of this will be posted on the Google Classroom, so you can track it down. Page numbers for your textbook. There's some really good videos here, and I think I found a way to actually start you guys at the right spot in these videos. Both of these crash course videos are really excellent if you want a little bit more information on what's going on. And then lastly, there's a worksheet that will summarize all of this stuff for you too, just a little bit of practice. And then I'm hoping next week we'll do a follow-up activity that will have you guys working your way through organic halides and some of the alcohols, carboxylic acids with concepts C6 and C7 that'll be coming up shortly next week. So without further ado, I think we're going to jump into looking first at, I'm going to drag this in here, looking first at our concept checklists, and I'm going to make my screen just a wee bit smaller so you guys can see me. So what we're working on over here, concept C4 is basically combustion reactions and having a look at what combustion reactions are, how they work, and bringing in a little bit of economically important fuels, those kinds of things with that. And then C5 is going to be covering organic halide compounds or organic halogens, and talking about what those are, how to name them and draw them using our IUPAC standards. Then we're going to talk a little bit about solubility as well with those, and I'll bring it up briefly for you. And then you guys will have a look at, we'll tie in that fractional distillation with all of this stuff. And then we're going to start to tie in some chemical reactions. So addition and substitution reactions we will be covering today as well. And so let's just jump ahead to this, and we will get rolling here. So, hey, my video stayed up there. That's a positive. All right. So, incomplete and complete combustions. That's what we're going to be talking about in this section. I'm just going to hide this because I think it is annoying. Let's hit the hide button and see how it goes. So, we are going to talk today first about complete combustion reactions. And what I should be able to tell you at this point is everything we've done so far in Science 10, in Chem 20, you guys, we've been doing complete combustion reactions. So a complete combustion, a hydrocarbon, some sort of a fuel, is reacted with oxygen to produce carbon dioxide and water vapor. And so you guys should understand that by now. This is something that is something that you guys have handled all the way through Science 10 and into Chem 20. So what we're dealing with in this complete combustion is a hydrocarbon reacting with oxygen, always in the presence of oxygen, to produce carbon dioxide. And I want to just highlight the water vapor bit because I think that's important. Recognize that this is water vapor because we're doing a combustion reaction. And when we did concept, I forget which concept it was in Unit A, we did talk about that when we do a combustion reaction, it produces water vapor instead of liquid water. Okay. So all of this is straightforward, simple stuff. We can communicate these reactions in word equations. We can do balanced chemical equations. We can do structural formulas now because you guys are able to draw those structural formulas. I'm just getting used to looking at my my video, and I'm wondering if I should move it at some point because it's kind of funny to see myself look back and forth and back and forth and back and forth. I'll figure it out. Maybe next week it'll look better. So we are going to write the word, balanced, and structural equations for the complete combustion of dimethylpropane. So if you wanted to hit pause right now and try that out, so the complete combustion of dimethylpropane, you're welcome to do it. Hit pause now to do that, and then I will jump in and get into having a look at what that looks like. So hit pause. Okay, and you're back. So this is what you should have come up with. So dimethylpropane, what you should have sorted out, here's our chemical formula for dimethylpropane. We've got one, this is a funny one because there's only one thing that can be dimethylpropane, right? You've got a 3-carbon compound. So depending on how you want to look at this, 1, 2, 3-carbon compound, right? With 2 methyls coming off of it. Or you could do a 1, 2, 3-carbon compound with 2 methyls coming off of it. So this is dimethylpropane. Reacting with oxygen, so that's what oxygen is going to look like, to produce carbon dioxide and water. Okay, and of course you could go and fill in, and we can do that right now. We can fill in here that this is going to produce 8 of those, this is going to produce 5, and this will produce 6 of those, right? We could fill all of that kind of stuff in, and that's what it's going to look like, complete combustion. Okay, just remember when we're doing a complete combustion reaction, if the carbon has an even number of carbons, you need to double what you have over here, but because dimethylpropane is C5H12, that's 5 carbons here, we don't need to double that. Okay, so that's plain and simple, fairly straightforward, I hope, for you. What we're going to move on to then next is we're going to talk about something that's a little bit different. Okay, so we're going to talk now instead about an incomplete combustion. And why we want to care about incomplete combustion is that it does affect our lives in some ways. Okay, it affects our lives in that we could be experiencing an incomplete combustion reaction, and it could actually threaten our lives. And so we'll talk just a little bit about that right now. So in the case of an incomplete combustion reaction, our hydrocarbon, or our, I'm going to have to move my video so I can see, our second hydrocarbon combustion reaction, carbon monoxide or soot or both can be produced in that reaction. Now let's just be clear on what carbon monoxide and soot are, right? Carbon monoxide we know is CO, okay? And soot, let's just be clear, is solid carbon. Okay, that's what we're dealing with when we're dealing with those kinds of reactions. So this would be carbon, and then we just write our solid afterwards. Okay, I'm at the edge of my screen on that, so we're not going to worry about that just yet. These can also be produced in conjunction with either of both carbon dioxide and water, depending on the situation we're dealing with. Okay. The incomplete combustion reaction of dimethylpropane might look like this. So here's our dimethylpropane again, okay? And it can produce carbon monoxide, or it can produce particularly just carbon, or soot in this case. So we could have either of these situations taking place depending on the situation. And then you can balance them accordingly, right? It's going to take, we'd start out with this and we go, okay, well, that's not going to quite work. We need to somehow end up with 12 hydrogens, and we're going to bounce back and forth a little bit for this to actually work and make sense as far as the balancing goes. Same thing down here, we may have to bounce back and forth a little bit. I'm very confident in your abilities to balance one of these reactions. What I want you to see and what I want you to understand instead is that we have carbon monoxide and or soot being produced in these reactions. So we're either going to produce carbon monoxide or we are going to produce soot in these reactions. It is an incomplete combustion when you see one of those two things as a product of a combustion reaction. Okay, so complete combustion, if you see carbon dioxide being produced, you know you have a complete combustion reaction. If you see carbon monoxide, or if you see carbon, or if you see pure carbon or soot in the reaction, then that's what we're dealing with. Okay, so we know we're dealing then with an incomplete combustion reaction. Okay, so I hope that makes sense. I'm going to switch to the next slide. So evidence shows that all three types of reactions, complete and the two incomplete, will take place when we burn a hydrocarbon. Notice, though, the fuel to oxygen ratio for each in each reaction. Okay, and I think this is really interesting. So let's just go back for a second. I made a typo on that slide, but notice here, okay, we have one part, we don't have a 1 there, but we have 1 part hydrocarbon fuel to 8 parts oxygen fuel. Okay, notice that there. Notice here that if we break this down, we have 1 to 11, okay, or sorry, 1 to 5.5, 2 to 11 or 1 to 5.5, depending on how you want to break that down. And then this is 1 to 3 ratio. So we have a 1 to 8 ratio here. We have a 1 to 5.5 ratio here and a 1 to 3 ratio here, fuel to oxygen. Okay. I made a typo here. This actually should be an 8, but it doesn't affect things. So in the complete combustion, it's a 1 to 8 ratio. In the incomplete combustion is a 1 to 1.5 ratio. In the soot reaction, okay, so this is the carbon monoxide reaction is 1 to 1.5. The soot reaction is a mere 1 to 3 ratio. So what this suggests is that if we maximize the oxygen available for combustion, we may be able to produce or reduce the chances of an incomplete combustion. So again, another way to look at this would be the more oxygen we have available, the more possibility that we're going to have a complete combustion. Okay, so as the oxygen levels drop, it's the better possibility of having an incomplete combustion. And why we care so much about this is because of this creature right here, this carbon monoxide and the carbon itself as well, but particularly this. You guys know, and we've talked about this before, that carbon monoxide is a dangerous gas, okay? And that dangerous gas has the possibility of producing or reacting with your body in such a way as for it to be very unhealthy for you or fatal, possibly. The way I'd like to look at it is, or not the way I like to look at it, the way it actually is that our bodies normally have hemoglobin that binds to oxygen molecules. And so those hemoglobin carry the oxygen molecules around our bodies and drop them off as we need them in our cells. And so those hemoglobin molecules, by the way, are located in red blood cells if you've done your biology. What ends up happening is carbon monoxide ends up wanting to bind to those hemoglobin molecules and does bind. But what happens is it's hard to get the carbon monoxide off of those hemoglobin molecules. So what ends up happening is we can't carry enough oxygen anymore because there's carbon monoxide holding on to the hemoglobin molecules. We can't get it off of there. And we end up suffocating from the inside. So that's a huge consideration for us. If we want our engines, for example, where we combust most of our hydrocarbons to run efficiently, then what we need to do is we need to ensure that they are burning enough fuel. Burning enough fuel with oxygen present, enough oxygen present. So large amounts of oxygen. And so we have to try to maximize that in some way. And so we have different ways to do that in our fuel systems. We may force the air fuel mixture to have high concentrations of oxygen in it by having oxygen in the fuel, for example. Anyway, something for us to consider as we move forward here is that carbon monoxide can be nasty and can be deadly. And you can see as the levels of carbon of oxygen drop, right? As that air-fuel mixture, the amount of air or the amount of oxygen that's around drops, then we can start to produce carbon monoxide, and that's dangerous. And then the soot here, think of it as the carbon junk that you get in engines, right? That can clog up an engine and cause issues too, especially if an engine is not working with enough oxygen in it for whatever reason. Maybe your air intake is blocked or partially blocked or something along those lines. Okay, so that's our discussion of combustion reactions. Really, really quick, really straightforward, I hope. That, we have two kinds of combustion reaction, a complete and an incomplete. Complete is what you have dealt with all the way through from Science 10 into Chem 20 and now to this point. And that happens with an excess of oxygen around. When we move into incomplete combustion is when we do not have excess oxygen around anymore for whatever reason. Could be that your engine is not getting enough oxygen to it. Maybe you're in a place that is lacking in oxygen, like a garage. Starting your car in a garage eats up all the oxygen that's in that garage, and you end up with a lack of oxygen in there. And that can lead us into producing an incomplete combustion, where we get carbon monoxide or even soot being produced. So that's really the big distinctions here for this particular concept. Now, what I'm going to do is jump really quickly to your notes, which I have minimized. Oh, there they are. Okay, and I'm going to drag them over, and I want to show you your notes. So this is the second half of Concept C4, and again, you've got a little bit of fill-in-the-blank work to do. Okay, so using pages 412 to 416, I want you guys to go through and have a look at what's in your textbook starting on page 412. The things I want you to pay attention to in this petrochemicals section. First, try to understand what a petrochemical is, okay? And then I want you guys to understand particularly what these words intermediates and derivatives are all about. And I'll just highlight them on here. So I want you guys to understand what intermediates and derivatives are, and understand basically what a primary petrochemical is. So what we're going to do is you're going to see you'll go from primary petrochemical to intermediates to derivatives. We are transitioning right now from where we were in the unit just dealing with hydrocarbons. So we dealt with aliphatics and aromatics, only compounds that are made up of carbon and hydrogen so far. Right now, this little self-directed stuff is transitioning you into dealing with compounds that don't just contain carbon and hydrogen. And those compounds are going to contain derivatives, okay? Those derivatives are compounds that have gone through reactions to get to them eventually. Okay, so I hope that kind of makes sense to what a derivative is. Dig into it a little bit deeper, but that's important. Understand a little bit about ethene and its derivatives and why ethene is so important, and we'll actually deal with it in the next section. And that's really all I want you guys to do. Then we're moving on to organic halides. Okay, so I'm going to drag this out of here, get rid of it, and move into the next bit. So that's your petrochemical stuff, working through your notes on your own. If you'd like to, have a look at 416 questions 1 and 2. And if you wanted to hit pause at this point and go and do those petrochemicals things, go and hit pause right now. And welcome back if you hit pause, and not welcome back if you didn't hit pause. What we're going to jump into now is concept C5. And C5 is dealing with organic halides and addition and substitution reactions. And honestly, guys, if you've made it through to this far and you've done relatively well so far, organic halides are not going to pose any problems to you. We're going to follow the same simple naming rules that we followed from concept C2 to this point. So we're going to go and we're going to start with our parent chain. We'll identify that. We'll determine if it's an ane or an ene or an ine. Then we'll start to build our way forwards by naming the branches. Now, the key bit to this is an organic halide is formed when one or more hydrogens are replaced by a halogen atom in the compound that we're dealing with. And recall, please, that a halogen is something that you find on your periodic table. Group 17 is the halogens, and I just happen to have mine right here. So remember, group 17 is over here, okay? and these are your halogens. So fluorine, chlorine, bromine, iodine, and astatine, although I've never seen astatine come up on anything just yet. And what I want you guys to understand is that these halogens are a functional group. So remember, I mentioned functional groups very briefly in the last concept. A functional group is something that identifies an organic compound as being a particular kind of organic compound. So if you have a triple bond, that means you're identifying the compound as being an alkyne. If you have an aromatic ring in it, right, a benzene ring, we are going to identify it as being an aromatic compound. If you have a halogen present, we can identify that compound as being an organic halide. Okay, so that's the functional group. A halogen present means it's an organic halide. Many of these compounds are toxic and carcinogenic, okay, meaning that we got to watch out for them, right? They could be very dangerous for us to consume, and if we come into a lot of contact with them, they can make us quite sick. So something for us to consider as we talk about these compounds. So we must balance the benefits and the hazards associated with them. Naming these compounds and drawing these compounds is very simple at this point, because we're going to consider, or use a branch for each one of the chloros, fluoros, bromos, or iodos that we're creating. So we're going to consider each of these things that we have on a compound. We're going to consider them a branch on that compound. So you'll have a fluoro branch, or a chloro branch, or a bromo branch, and so on. So these are branches. So we'll name them as we would any other branch, a methyl branch, an ethyl branch, whatever it might be. So remember, we're going to name these by doing the parent chain first and then building our way backwards in the molecule. If we have to draw these, we're going to identify the parent chain, draw that first, and then add them onto it. Okay, so I'm going to drag this up over here again, and we're going to have a look at what we've got. So just to give you an example, so dichloroethane. So I've and if you're paying attention, I've got a typographical error on here. There should be a hyphen after the two there. So let's go cheat our way in here, and we'll just draw that hyphen in there. So there should be a hyphen right there. 1, 2 hyphen dichloroethane. Okay, so this is what we would do, is if we're going to draw this, I would start at the end here with the ethane. Eth means 2, ane means a single bond between those two carbons. So we end up having the two carbons drawn out. And then what I would do is jump here and see I have a dichloro. Okay, where are those chlorines located? Well, they're located on carbons 1 and 2. So then I would draw a chlorine on carbon 1 and a chlorine on carbon 2, and then fill in my hydrogens. Okay, so I hope that makes sense to you and how that works. So then what would we call this? So let's start out first. Now don't get confused here. This is the one thing I want everybody to watch out for as we move forward here. The way this is drawn, okay, I need a different color here. The way this is drawn is that we've got carbon 1 here, carbon 2 here, 3, and 4. Okay, and that there is no carbon here or no carbon there. This is just showing that this is a carbon here, okay, with a branch, with a bromine branch coming off of it. Okay, so then how we're going to deal with this is we are going to write this out by starting with our parent chain. So we will be counting then our carbons. There are I'll show you with my little highlighter here. There are 1, 2, 3, 4 carbons. 4 carbons then means that it is a but, B-U-T. Okay. All of the bonds are single bonds between the carbons, so it is a butane. I apologize for the terrible writing. Now, we have 4 bromines on here, so I'm going to put bromo. Okay, and if you don't remember, it's tetra is 4. So it's a tetrabromobutane. And then I'm going to have to write this above, but normally you would write this in front of this. We have to identify the location. Remember, we're going to treat each of those bromos as a branch. So we have to identify the location of each of those branches. So it'll be a 1, comma, 2, comma, 3, comma, 4, right? Because there's a bromine on carbon 1, a bromine on carbon 2, 3, and 4, and then a hyphen. So 1, 2, 3, 4, hyphen, tetrabromobutane. That's as hard as it is, okay? The only things that might get a little wacky, don't forget, is you may end up having a couple of halogens on each of the in a compound. So you might have a chlorofluorobutane, in which case, if you have a chlorofluoro or a bromo-iodo, always list the branches in alphabetical order, like we've done before. And don't forget your dis, tris, and tetras if you have them. Okay, so nothing more complicated than what we've done before on this stuff. So next thing we're going to move on to then is we are going to hopefully go to the next page. So what I want to do now is just do a quick bit on the two kinds of reactions that are associated with this. And why we do it here is it just kind of makes sense for us to do it at this point. Now, don't forget the term unsaturated hydrocarbons. Unsaturated hydrocarbons react with small diatomic, sorry, I'm going to circle back. An unsaturated hydrocarbon means that it's a hydrocarbon that has a double or a triple bond in it. In other words, it doesn't have as many hydrogens on it as it could have. It is not saturated with hydrogens. So an unsaturated hydrocarbon in an addition reaction reacts with small diatomic molecules such as bromine or hydrogen, and what we get is we call it an addition reaction. Okay, so an addition reaction is when an unsaturated hydrocarbon reacts with a small diatomic molecule. And really, guys, this is super, super important to be able to recognize this. So if you have an unsaturated hydrocarbon that's reacting with a small diatomic molecule, it's an addition reaction. And how it works is relatively straightforward, okay? So I'm going to get my right pen color here. All we're doing is imagine down here at the bottom where we have ethine, and that's what we're dealing with. It's reacting with hydrogens, and it's eventually going to end up producing ethane. And what's happening at that point is it's gone through a couple of really quick reactions. Oh, and by the way, this little nickel here means it's a catalyst. Okay, so it's included above the arrow because it's a catalyst. Remember, catalysts don't participate in the reactions, and all they're there to do is lower the activation energy. Okay, so the triple bond here goes down to being a single bond. And so what ends up happening is we break this double bond, or this triple down to a double bond. And then I'm going to put a couple of dots here. Okay, those dots represent bonding electrons. Okay, hydrogen over here is this. So in the first sort of run through of this, the hydrogen bond between the two hydrogens is broken, also freeing up a bonding electron on each of those. And so this hydrogen goes and attaches on that bonding electron. This hydrogen goes and attaches on that bonding electron, and we've created ethene from ethine. Okay, then what'll happen, the next thing is this bond here will get broken, and that other hydrogen molecule that we have over here, right? We have two hydrogen molecules, there's one of them. It has its bond broken. We create another set of bonding electrons on each of these. And then this hydrogen goes and ends up bonding to that carbon, and this hydrogen goes and ends up bonding to that carbon. So we've gone and we've added 4 hydrogens to that ethine molecule by breaking the triple bond down into a double bond and breaking the double bond down into a single bond. That is an addition reaction, where you break a bond, a double or a triple bond, and free up bonding electrons so that a small diatomic molecule can insert its stuff on there. What is key is to remember that where we break the double and triple bond, that frees up a bonding electron on each of the carbons attached to that double or triple bond. And that means that our small diatomic molecule will attach one atom to each of those spots where we freed up the electrons. So if we added chlorine to an unsaturated hydrocarbon like ethene, we would end up with a chloroethane of some description. So this is ethene reacting with chlorine. So remember, we're going to break that double bond and break that bond. That frees up a bonding electron here and here, as well as here and here. And so that chlorine attaches there, this chlorine attaches there, and we end up with 1,2-dichloroethane. Okay? And we have to do the 1 and the 2 because we could have a 1,1-dichloroethane, right? But we have in this case a 1,2-dichloroethane. The same can be said for other halogens that are out there. Remember, we can also add hydrogen halides as well to unsaturated compounds, which produces interesting structural isomers since the halide molecules can bond in different orientations, right? You could end up with the halogen on carbon 1, or you can end up with it on carbon 2. Really depends on the situation. What I've done here is a couple of examples of addition reactions, okay? Now, before I get into explaining the reactions, I did want to just take a second to get you guys to understand how to recognize that you're dealing with an addition reaction. Just to remind you, in each of these, if I just gave you the reactants, ethene and bromine, what would draw me to this being an addition reaction is that we have an ene here. There's also an ene there, right? And this is an ine. Any unsaturated hydrocarbon reacting with, again, a small diatomic molecule, okay, then we end up with an addition reaction, okay? So if you see an ene or an ine in the reactants and a small diatomic molecule, you've got an addition reaction. And then all that means is we're breaking the double bond, breaking the bond in the small diatomic molecule, and then attaching, in this case, the bromines to the compound where those bonds were broken between the two carbons, okay? And this makes a 1,2-dibromoethane. In this case, we have a 1,2-dibromoethene. We're going to break this bond. We'll break the bond between the bromines there, and we end up with a 1,1,2,2-tetrabromoethene. Sorry, let's say that again. 1,1,2,2 tetrabromoethane. Not an ene, it's an ane because we've broken that double bond. Now, I'm going to move myself up over here, and we'll have a look at this last one. And this one I've broken up into 2 steps. So first things first, we're reacting ethine with fluorine. So we're going to break that triple bond now down to a double bond. And technically there would be 2 of these. Okay, we'll break that, and we create a 1,2-difluoroethene. And then we're going to break that again, add the second one of these fluorines to the spot where we broke the bond, and we end up with a 1,1,2,2 tetrafluoroethane as our final product. Hope that makes sense to you. Relatively straightforward. The trick to doing these reactions is recognizing what kind of reaction it is. I have, in these cases, unsaturated hydrocarbons reacting with small diatomic molecules, so I know that each of these is an addition reaction. The last kind of reaction that we're going to cover today is a substitution reaction, and involves breaking a carbon-hydrogen bond in an alkane or an aromatic ring. So automatically, we've got another way to recognize that we're dealing with a substitution reaction. In an addition reaction, we were dealing with an alkene or an alkyne. Now we're dealing with an alkane or an aromatic ring. Okay, so what we're dealing with then are aliphatics and aromatic. Sorry, that's a lie. We're dealing with alkanes or we're dealing with aromatic rings, only carbons and hydrogens on them already. Okay, and then we're replacing the hydrogen atom that we broke off with another atom or group of atoms. Okay, these often occur slowly at room temperature, so light may be necessary for the reaction to take place. And note, there may be more than one possibility for where the halide group replaces. Okay, so there may be more than one possibility. And so we may end up with some isomers of something. So we may end up with a 1-bromo or a 2-bromo or a 3-bromo, depending on which hydrogen is actually getting broken. Okay, usually what happens is the compounds aren't equally represented, and so you end up with a whole bunch of one and a tiny amount of another. So this is an example here where we have, I'll just get my red pen back, where we have propane, 1, to three carbons in a row, so that makes it propane, only carbon-carbon single bonds. We're going to remember that these are actually H. There'd be an H here and an H here, right? There'd be two H's here. But what's going to happen is we'll end up breaking a bond here, for example, breaking a bond here. And so one of these bromines will come over and swap places with the hydrogen. So these guys will swap places. And so we end up with this example here, where I have a bromine coming off of this carbon and then an HBr left over. The other possibility is that one of the hydrogens over here, remember there's a hydrogen here and a hydrogen here. The other possibility is one of those gets broken off and then a bromine swaps, okay? And we end up with this kind of thing. So here we would have a 1 bromopropane, and this one we would have a 2 bromopropane. There is no such thing as a 3 bromopropane because all you'd have to do is take that molecule, turn it around, and it becomes a 1 again. Okay? In the second example here, we have benzene. So we have a regular benzene ring. Remember, each of these has a hydrogen coming off of it, right? I've just drawn the line diagrams, but each of these has a hydrogen. So again, in a substitution reaction, we are going to substitute a hydrogen for something else. So we're going to break off that hydrogen, and we'll break apart that molecule. This chlorine and that hydrogen will swap places, okay? And we'll end up with a chlorobenzene and a hydrogen chloride left over, okay? So addition reactions are where we're taking a double or triple bond and adding something to it, a small diatomic molecule. A substitution reaction is where we're breaking a carbon-hydrogen bond and substituting the hydrogen for something else. Okay, usually a chlorine or a fluorine, some halogen. But we're going to see elsewhere there are other kinds of substitution reactions out there. So that is it for this, this lesson. So we're a little under 40 minutes right now. That's concepts C4 and C5 covered for you. So there's some practice questions here, and then I'm just going to tab myself back over to here. Nope, that's not where I wanted to go. There it is, back here. And just to remind you, there's a couple of videos that I think are pretty valuable for you guys to watch. And I would recommend, if you want to go back right now and watch all 3 of these videos, really, this one is a 9, maybe 10-ish minute video, but you're really starting at the 9th minute, so it's not too bad. This one's 5 minutes long, really quite good. And then this one is also really quite good as well, and you're jumping in at 4 minutes and 40 seconds approximately. Okay, please go and have a look at worksheet number 3 as well and do the questions on there. It'll have you looking back a little bit at concept C2 for a little bit of review, which is excellent, and some C3 for a little bit of review, which is excellent. And then we jump into the halides. Don't do the end. If you get into something that says OH at the end of it, a little branch with an OH on it, that's an alcohol. Skip that for now. We'll circle back to that after we've done the next lesson. Jump onto your practice quiz when you're done that, and then please wait for my feedback on your practice quiz before you head on to your summative assessment. So that is it for me today. I hope you guys have got something out of this. As always, if you have any questions, please come by for my office hour or fire me an email. I'd be happy to answer your questions. Stay healthy, and we'll talk soon.